Good morning. Welcome to topic number 11 on radiation intensity U and numerical on radiation intensity and directivity gain calculation. We have already discussed in topic 4 that radiation intensity U is power per unit area or power per unit solid angle, which is defined as watt per steradian. Now let's recall this concept and define it from power theorem. So power theorem states that the Poynting vector SR is the power radiated by an antenna over a surface of sphere having radius r. So it is P divided by 4 pi r square. Now if we rearrange these terms, we get P divided by 4 pi as r square into SR. The reason we have rearranged this term P divided by 4 pi because it looks like radiation intensity. This term is nothing but radiation intensity because it says power per unit solid angle and 4 pi is solid angle subtended by sphere. So this term represents power per unit solid angle since 4 pi is solid angle subtended by a sphere. So we can call P divided by 4 pi as radiation intensity U, and its unit, as we mentioned earlier, watts per steradian. Applying this concept to an isotropic antenna, we get P is equal to 4 pi into U. But since we are talking about an isotropic antenna, we can always mention it as average power U0. So U0 becomes average radiation intensity or you can call it as radiation intensity, right, in short, radiation intensity for isotropic source. So let's now solve one example to find beam area, and from beam area computation of directivity and gain. So the statement of numerical is here. It says calculation of only beam area. Find the beam area if the antenna has field pattern. You can see here the example gives field pattern. It's not power pattern but field pattern, and it is given by E of theta equal to cos square theta. E is always dependent on theta and phi, but here in this example we have taken only one variable, one angle, which is polar angle E of theta, and the field pattern term is cos square theta. Theta is ranging between 0 to 90 degrees. So the formula for finding beam area omega A is double integral phi ranging from 0 to 2 pi. Phi always varies from 0 to 2 pi. It is azimuthal angle which is for the entire sphere along the equator, and theta, as mentioned, is ranging from 0 to 90 degrees, pi by 2. But in the calculation of omega A, beam area, the term considered inside the integral is normalized power, which is function of theta comma phi, multiplied by d omega. D omega, as I mentioned earlier, is the incremental area subtended by a small region dA. Sin theta d theta d phi is d omega. Now, in order to find the power, because power is not mentioned in the numerical, electric field is mentioned. In order to find the power, we need to take the square of electric field term. But even before taking the square of electric field term, let us normalize the electric field because we need normalized power. So to normalize the electric field, we divide the given electric field by its maximum value. So En of theta is E of theta divided by E theta max. Now as you can see, the field pattern term is cos square theta, and the theta range is between 0 to 90. As you know, cos 0 is 1 and cos 90 is 0. So the maximum radiation, which is 1, we can get only in the direction of 0. Therefore, the maximum value of electric field in 0 direction is 1, and the given E of theta is cos square theta. So cos square theta by 1, we get the normalized value also cos square theta. Now, as I mentioned, we need the power here. You need to be careful, because in few examples there will be electric field mentioned, and in few numericals or few examples there will be directly the power per unit area, or the power density, or which we also call radiation intensity, will be mentioned. So you need to be careful when the value of field pattern is given or power pattern is given. Since field pattern is given here, we substitute in place of power field square. So normalized value of En of theta, it's square, and this d omega term as it is sin theta d theta d phi, and the value of En of theta is cos square theta, and its square will become cos raised to 4 theta. So this is the field term inside the integral, and sin theta d phi is d omega term. Now as you can see here, we have to solve this double integral, and then there is no term mentioned for phi variable. So we can take phi separately, integrate it, substitute the given limit, and we get the answer 2 pi. Now the task is to find out this integral. The integral of cos raised to 4 theta sin theta d theta. The given limit is, for theta, you can see here 0 to 90. So 0 to pi by 2. So you have learnt integration. The simple substitution technique we use here. We substitute in place of cos theta x, and if we differentiate, we get x differentiation dx, and cos theta as minus sin theta d theta. Now we need to replace the limits also. So when we see the value of theta is 0, we get cos 0 as 1, and when cos theta is pi by 2, the answer we get as 0. So these are two new limits which we need to use in the integral. So omega a we compute 2 pi, constant outside the integral. For earlier limit 0, the new limit is now 1. From 1 to 0, we need to find the integral of x to the power 4 dx. So x to the power 4 dx, we can take minus term sign, minus sign outside the integral, and find the integral of this, which is x to the power 5 by 5. Here I have solved the integral. Omega a as minus 2 pi x to the power 5 by 5, and the limit 0 and 1. So if we substitute the limits, the answer that we get for beam area is 2 pi by 5, and the unit for beam area is steradian. Now this is one procedure by which we have found only omega a, but our aim is to find the directivity further. And as you know, directivity from beam area is defined as 4 pi by omega a. 4 pi is the beam area subtended by a sphere, and omega a is the beam area subtended by the given practical antenna. In our case, omega a, beam area subtended by the given practical antenna, is 2 pi by 5. So if we do the substitution, 2 pi by 5, we get the directivity as 10. Let us solve one more example now, but in this case the field radiated by an antenna is not given, the radiation intensity is given. So the radiation intensity of an antenna is given by U, and in this case the term says it is um cos square theta. If you see the previous equation, the value of electric field E of theta was given as cos square theta, but now it is cos square theta. U is radiation intensity, which is nothing but power per unit solid angle, and stands for the maximum radiation intensity. So cos square theta is the value given, and theta is again ranging from 0 to pi by 2, very similar to previous case, and phi ranging from 0 to 2 pi. Now we need to compute directivity and gain if efficiency is given. Efficiency is 0.95, which indicates 95% efficient antenna. So we are now applying the power theorem. Power theorem tells us the procedure to calculate the power radiated by the given antenna when its radiation intensity is known, which is cos square theta and sin theta d theta d phi. The limits of phi and theta ranges from 0 to 2 pi, and for theta 0 to pi by 2. So if I show you what we have done in the previous example, we computed beam area. In case of beam area, the limit was same, it was double integral. We mentioned the normalized power radiated by antenna and sin theta d theta d phi. But now we are not finding beam area, we are finding the power radiated by given practical antenna having radiation intensity cos square theta. So there is no question of squaring this cos square term, which in previous case we mentioned as cos raised to 4 theta. So now the question is to find the integral of cos square theta sin theta. This term being constant, because it is representing the maximum radiation intensity, it will be out of integration, and we need to integrate phi from 0 to 2 pi, the term d phi. There is no term related to phi here, and now the task is to find the integration for cos square theta sin theta d theta for limit ranging from 0 to pi by 2. So the integration of this is 2 pi, and we need to find the integration of cos square theta sin theta d theta for theta ranging from 0 to pi by 2. So we follow the same procedure what we did earlier. We substitute cos theta is equal to u, and we get the differentiation of this as sin theta d theta equal to du. And since we have a sin theta d theta term here in the integral, we mention this as sin theta d theta equal to minus du. Upon substitution, the power radiated by the given practical antenna, we get u square minus du, because sin theta d theta is minus du. So I'm sorry, this term 2 pi and is there. So 2 pi minus 2 pi and integral of u square du. So next, what I missed here is the changing the new limits. When theta is 0, the value of cos 0 is 1, and when theta is pi by 2, cos 90 is 0. So these are our new limits, 0 and 1, with which we have done the integration. So the answer should be, now I continue here, the power radiated by the given antenna is minus 2 pi into bracket. If we do the substitution of u limit values 0 minus, I hope you can see this, it's 1 by 3. So this minus and this minus 1 by 3 will become plus. So the power radiated by the given practical antenna comes 2 pi by 3 This is our first equation we have computed from the integration. So let me write the power radiated by given source or given antenna is 2 pi by 3 um. Now can you please go back to 158. 158 means I mean 1 minute 58 seconds of this video, and check. We have written one formula for the power radiated by an isotropic antenna as P is equal to 4 pi U0, where U0 indicates the average radiation intensity. Now if we compare these two equations, the power radiated by the given practical antenna and power of an isotropic antenna, we get 2 pi by 3 um equal to 4 pi U0. If we take this U0 term in the denominator, then we get 4 pi divided by 2 pi by 3. Pi cancels. We get the answer as 6. So the question is, why we have taken this ratio of um and um to U0? The reason is, this ratio is indicating directivity, because the definition of directivity says that it is a ratio of maximum power to its average value. So U is radiation intensity, which is nothing but power per unit solid angle, and U0 indicates its average value. So this directivity is nothing but ratio of maximum radiation intensity to its average value. Now from the directivity value, directivity is a unitless number. From the directivity value, the second term can be calculated, which is gain, as product of efficiency and directivity. The given antenna is 95% efficient, so K is 90.95. Therefore gain is 0.95 into 6, which comes 5.7. So if we want the value of gain in decibel, we need to take 10 log of 5.7, which comes as 7.56 dB. So from the given statement, radiation intensity pattern was given. It was not field pattern, it was radiation intensity pattern, which is power. So we considered the power term directly here. No square was done like previous numerical. So cos square theta was substituted, and the integration of cos square theta sin theta was computed separately. Term retained in the example as it is, so that we can make use of it at the end to bring it in the form of a formula of directivity, which is by U0. Directivity is the maximum radiation intensity to the average value or radiation intensity of an isotropic antenna. You can say this is maximum radiation intensity and this is radiation intensity of an isotropic antenna. So in this way, in this video, we have discussed different examples solving radiation intensity, calculating directivity and gain. Another numerical we solve here for a lossless resonant half wave dipole antenna with input impedance of 73 ohm and transmission lines characteristic impedance of 50 ohm. So you can imagine a situation where an antenna is connected to a transmission line and the input impedance is 73 ohm and the transmission line's characteristic impedance is 50 ohm. So definitely there is an impedance mismatch here because both the values are not same. And the radiation pattern of this half wave dipole antenna is U is equal to U0 sine cube theta. If you see the previous example, it was U equal to UM and some cos or sine term, but here the textbook or the author refers this UM term as B0. So now you have to find the maximum realized gain of this antenna. So the solution of this example starts with the same equation of finding the maximum radiation intensity, which is equal to B0 here. So this B0 in fact is UM. It's written here Umax, but it is UM. Then we follow the same procedure. We find the power radiated by this given half wave dipole antenna by making use of this double integration, which is for limits phi ranging from 0 to 2 pi and theta from 0 to pi, with U radiation intensity as a function of theta comma phi. This is a normalized value, and sine theta d theta d phi is d omega. Now this integration part is left to you as homework. You can see 0 to 2 pi, since there is no phi term, 0 to 2 pi d phi integration is 2 pi. U of theta comma phi, this b0 itself is a term. It is taken out of the integration because it is constant, and our u of theta comma phi, the remaining term is sine cube theta. When we substitute it here, it is sine cube into sine theta becomes sine raised to 4 theta d theta. The integration of sine raised to 4 theta d theta for limits 0 to pi is a homework for you. I expect you to solve this derivation, this integration, and when we interact on Zoom, I will ask you your experience in solving these integrations. So the B0 term remains as it is, which is in fact a term, and the integration we get is 3 pi square by 4. Now this radiated power can be equated to the power radiated by an isotropic source, which is 4 pi u naught, and we get the directivity as you can see 4 pi term here and 3 pi square by 4 term also taken here. You can solve this particular equation and see the value obtained for directivity is 1.697. Now in the previous example, the efficiency of the antenna was given, so finding the gain was a straightforward task, because gain of an antenna is defined as product of efficiency and directivity. But in this case, efficiency of antenna is nowhere mentioned. We need to compute the efficiency first and then go for computing the gain. So the process of finding efficiency is very important here. We can see in this case, although efficiency is not mentioned, we can assume there are 3 types of efficiencies, and the product of these 3 efficiencies is the total efficiency. So these 3 efficiencies, as I mentioned in the previous video, are conduction efficiency, dielectric efficiency, and reflection efficiency. The conduction and dielectric efficiency cannot be calculated, but it is experimentally found. So in this numerical, we assume that the efficiency for conduction and dielectric ECD is equal to 1. Thus, the total efficiency is nothing but the efficiency computed for the reflection ER, and it is given by a formula 1 minus gamma square. Gamma is reflection coefficient. We can see here the reason for assuming the radiation efficiency ECD equal to 1 is it is mentioned that the antenna is lossless. So most of the errors or most of the losses related to conduction and dielectrics are assumed 0. So efficiency is 100%. Now to find out the gamma, this gamma calculation we have done it in the first unit. It is Zin minus Zo divided by Zin plus Zo, and since it is gamma square, it is 1 minus gamma square gives us 0.96. So the efficiency, radiation efficiency, can be computed in dB by taking 10 log of this 0.965, which is minus 0.155. So the overall efficiency, now you can see it is the product of all 3 efficiencies. Conduction and dielectric efficiencies clubbed together, and it is 1. And the radiation efficiency is 0.965. So the total efficiency is 0.965. In dB it is minus 0.155. So the maximum realized gain is equal to the product of total efficiency, which is 0.965, and the directivity we have computed 1.697, and the answer is 1.6376. and in dB it is 10 log of 1.6376, which is 2.142. So in this video is a long video. We have solved many numericals on computing the directivity and gain from the given radiation intensity. So in the next video we will learn how to find directivity and gain from HPBW using approximate directivity formula. Thank you.